In this lecture video, we will first look at vector representations and then vector computations such as addition, subtraction, dot product, and cross product. So let's get to it. When you think about vectors, you have to keep in mind two important aspects. One is the magnitude, the other one is its direction. We will use some unit vectors to represent this. I pointing in the x direction, j pointing in the y direction, and k pointing in the z direction. And each unit vector has a length 1. So let's try to represent a vector in two-dimensional space. A vector is drawn with a line and an arrow attached to it. Let's first represent this vector using its components. X component, y component. So then we can represent this vector by Vx in the I direction plus Vy in the j direction. And we call this form of representation rectangular form. We could also represent the same vector using its magnitude and the angle. Let's do this by recognizing this is a right angle triangle and the angle formed between the vector and the x-axis is represented by theta. So then vector v can be represented by its magnitude, that is the length of the line, and its angle theta. And this form of representation is called the polar form. Conversions between the two forms are quite convenient. Let's see how it's done. If we know the magnitude and the angle, we will be able to find its component using trigonometry, and the cosine angle times the magnitude gives us the x component, and the magnitude times sine of the theta angle gives us the y component. If you know the component values, the magnitude can be computed by using the square root of the Vx squared plus Vy squared. Theta angle can be calculated as the arctan of the ratio of the two components Vy over Vx. With this knowledge, we can now look at vector addition. Let's use a two-dimensional space to illustrate this. The first vector, vector A, we can describe the vector by its component. And the second vector, vector B, we can also represent by components like this. To perform a vector addition, draw a parallelogram connecting from the tail to the tip, and this is a vector sum of the two vectors. And in component form, we are performing the summation in the xy directions. Let's try a vector subtraction. Again, in two-dimensional space, we will do A subtract B. First, we will do a negative B vector pointing in the opposite direction of the same lens, then performing the usual parallelogram. And that's A subtract B vector in graphic representation. And by its component, we are performing subtraction in each of the x and the y components. Now we're ready for the dot product between two vectors. Let's try to draw vector A and B and mark the angle between the two vectors. To perform a dot product between A and B, we will need some helper equations. We will look at how to perform dot product between two unit vectors, I dot I or j dot j or k dot k. Noticing because they are all identical vectors, the result will be a 1 if we were to perform dot product between two orthogonal vectors. We will end up with a result of 0. This is because dot product will produce a scalar factor. The result of it is dependent on the cosine of the angle between the two vectors. We can now come back to perform a dot product between those two vectors A and B. This time I'm writing the vectors in three-dimensional form, and using the helper equations, we will see the end result of the dot product between A and B is a scalar quantity like this. Finally, let's look at cross product between two vectors. Cross product of A and B vectors will produce a result that is also a vector, and let's call that A cross B vector. And the direction of that vector happens to be perpendicular to both the A vector as well as to the B vector, indicated by this. Let's describe the cross product of A and B by writing out the three-dimensional component form. And this time, let's write out also the helper equations. Cross product will produce a vector form whose magnitude depends on the sine angle between the two. Let's first look at the cross product between ij, between jk, and between ki. Noticing that if we were to reverse the order of the cross product, the result is different by a negative sign. With this knowledge, we can now perform cross product between A and B, and the result will be written in component form: I component, j component, and the k component. And noticing that the magnitude can be represented by the product of the two vectors multiplying by the sine angle. And the best way to represent the direction of a cross product is by the right-hand rule. We will use the index finger to indicate vector A and the middle finger to indicate vector B. And the result of the cross product will be indicated by the thumb perpendicular to both the index and the middle finger as such. Thank you for watching.